Good morning, everyone. My name is Burke Kanemasu, and today my partner Daniel Escudero and I will present our thesis entitled Achieving Bell-Shaped Lift Distributions with Hydrofoils of Anisotropic Construction. Before we begin, we would like to thank our principal advisor, Professor Royce, for his invaluable guidance throughout this process. We would also like to thank our reader, Professor McMahon, and our editor, Professor Harris, for their help polishing our written document. I'll begin by reviewing the relevant theory and prior work. I will then state the objectives for our thesis project and describe the methodology that we use to achieve those objectives. At this point, I'll pass the presentation off to Dan to discuss our iterative analysis, followed by our results and conclusions, and finally, make some recommendations for future work. We first need to define some basic terms to use to describe the geometry of the foil. On the left, you can see a plan view looking down of a foil, and on the right, you can see a profile or 2D section view. Starting off with the extents of the foil, the leading and trailing edges are the foremost and aftmost extents. The tip is the outermost end of the foil, while the root is the innermost end, which is typically fixed. The chord length is the distance between the leading and trailing edges parallel to the direction of flow. The span is the distance between the root and the tip in the direction perpendicular to the flow. Moving on to the 2D section, we have the chord line, which is formed by drawing a straight line between the leading and trailing edges of the section. The thickness, which is the vertical dimension between the bottom surface and the top surface of the foil. And the camber, which is the distance between the chord line and the mean camber line. The mean camber line is formed by taking the mean or average between the top and the bottom surface. Now that we have defined some basic terminology, we can move on to the underlying theory behind this thesis. Going back to 1933, when Prandtl published a paper aiming to minimize induced drag for wings. In this paper, Prandtl utilized lifting line theory to compare foils with elliptical and bell-shaped lift distributions. Lifting line theory, which Prandtl developed himself just over a decade earlier, it was the first analytical tool that could be used to calculate lift of a finite wing with arbitrary planform and twist. The analytical nature of this calculation allowed for optimization by way of minimizing induced drag for a set of constraints. Using this methodology, Prandtl theorized that an elliptical distribution was best for a fixed wingspan, whereas a bell-shaped distribution was best for a fixed root bending moment. Taking a closer look at this comparison, we can see that for the same total lift force and root bending moment, a foil with a bell-shaped lift distribution will be 22% longer and have 11% less induced drag when compared to the same foil with an elliptical lift distribution. What we're really getting at here by using a structural constraint, such as constant root bending moment, is a constant structural weight of the foil. One way to think about this is a way of increasing the aspect ratio of the foil without compromising weight or lift. Aspect ratio is the ratio between the span and the chord. Increasing this ratio has an inverse effect on the induced drag coefficient, as can be seen from the equation shown. In 2020, Pierce and Tennell aimed to take advantage of this very effect by achieving a bell-shaped lift distribution using a rigid twisted foil. They performed their analysis of hydrofoil performance in XFLR5 using the vortex lattice method. This is an inviscid numerical method, which is highly efficient but requires a viscous correction. They found the results of this analysis were consistent with Prandtl's theory, and they also noticed that the twisted foils produced weaker wingtip vortices, which could be another source of efficiency gain. While Pierce and Tennell achieved their bell-shaped lift distribution with a rigid twisted foil, this can also be achieved through bending torsion coupling. This is where the use of anisotropic material comes into play. While isotropic materials have the same physical properties in all directions, anisotropic materials can have very different physical properties depending on which direction you measure. In this case, highly anisotropic materials, such as unidirectional fiber composites, can cause intentional bending torsion coupling in the foil. The lift force acts on the foil like a cantilever beam, which generates the necessary bending moment for twist. In 2018, Julie Young showed that this bend-twist coupling could in fact be utilized for symmetric foils. She tested 3 foils with identical geometry, but varying anisotropic construction. She tested one foil with nose up twist, meaning that the leading edge twists to increase angle of attack, one foil with nose down twist, meaning the leading edge twists to decrease angle of attack, and one foil with no bend twist coupling. The results of her flow channel testing showed that the nose-down coupled foil had reduced hydrodynamic load coefficients and delayed stall. The objectives of this thesis are to first design a laminate schedule for an asymmetric hydrofoil that results in bending torsion coupling at the foil tip, and then to determine which of several variants in construction maximizes performance and comes closest to a bell-shaped lift distribution. So how can we utilize bend-twist coupling to achieve our desired lift distribution? We start out with an elliptical plan shape and systematically tune the composite layup to approach the proper nose-down twist until we observe the bell-shaped lift distribution. The equation for chord length for an elliptical planform is shown alongside a high-performance composite hydrofoil that utilizes this planform. The procedure we use to obtain the performance characteristics of the twisting foil is to first start with a foil geometry and laminate schedule that we would like to test. Next, we find the pressure distribution on the undeformed foil at the predetermined design speed using a numerical analysis. We can then apply the pressure distribution to a finite element model of the foil. This model will solve for the deformation and stresses of the foil under the lift load. Since the twist of the foil will affect the pressure acting on it, the deformed foil geometry needs to be then reanalyzed. And the process is repeated until the change between iterations is negligible. While searching for an asymmetric foil section to use for this analysis, we had two main criteria. Most importantly, we wanted to choose a section that had high performance at our operating speed of 4.4 meters per second, meaning a high lift to drag ratio at relatively low Reynolds numbers. The second characteristic we looked for is a drag bucket, where the drag drops significantly within a range of angles of attack. Our thought process for this is if the foil can tap into this angle of attack range while twisting, the performance gain may be even more exaggerated. Based on these criteria, the foil selection that we chose to analyze was the Wortmann FX60-100 airfoil. This foil section meets all of our criteria and also has the added benefit of a particularly strong nose-down pitching moment that can also contribute to twist. Now that we have determined the geometry of the foil, the next step is to choose the laminate schedule that we would like to test. We chose to use a 5-layer laminate schedule consisting of 4 layers of unidirectional fibers and 1 layer of thin cloth around the outside surface of the foil. From here, we focused on changing the angle of the unidirectional fibers to optimize for bend twist coupling. With the foil defined, we can now start looking at the analysis. We begin by analyzing the undeformed foil with the vortex lattice method in XFLR5. This is similar to how Pearson Tennell performed their analysis in 2020. The reason we chose to use this method instead of lifting line theory is that lifting line theory only provides lift along the span and does not calculate a pressure distribution. Because vortex lattice method uses discrete panels for its calculation, a convergence study was performed to determine the most efficient panel size. Dan will touch on this more as part of error analysis. XFLR5 works by using 2D performance coefficients of the foil section and the 3D finite wing effects to efficiently calculate lift distribution, drag, and forces on the foil. Here you can see the lift distribution for an undeformed elliptical foil. For the purposes of this iteration, the most valuable output of the analysis is the pressure distribution. Since SolidWorks only allows pressure distributions to be inputted as an equation, we must first determine the equation that describes the pressure coefficient as a function of x and y coordinates. To accomplish this, we used a MATLAB script to fit a surface to the exported data points. It's important to note that XFLR5 mirrors the foil around the root for this analysis. For efficiency, we only model half the total wingspan, which is sufficient since it's perfectly symmetric. To create our finite element model within SolidWorks, we first start with a solid element core, then we bond shell elements throughout the top and bottom surfaces of that solid element. The solid core is a 3-dimensional element representing the foam core of the foil, while the surfaces are 2-dimensional elements representing the fiberglass laminate that encapsulates the foam core. Each of the 2 shell elements is assigned a layup schedule, consisting of individual layers of composite, which are each assigned their own thickness and fiber angle. With just these 3 bonded elements, we now have a representative model of the hydrofoil that we can use for finite element analysis. Before we can hit run on the analysis, however, there are still some things we need to set up. We need to create a pressure load and distribute it according to the best fit equation from MATLAB. We also need to fully fix the root of the foil as if it was attached to the mast of a T-foil arrangement. Finally, we need to mesh each element we created. We used a consistent mesh size for all three elements that was determined through a convergence study. Once the model is fully set up and meshed, we can solve for displacements and stresses. The model in XFLR5 can then be updated with the deformed foil geometry, and the entire process is repeated. Foil deflections and pressure distributions converge quickly and clearly, dropping to sub 1% changes within just a few iterations. Once converged, we're left with the deflections and hydrodynamic coefficients of our foil at steady state. I would now like to invite Dana to present on the convergence studies performed.
Thank you, Burke. A convergence study was conducted for the SolidWorks FEA to find a sufficiently small mesh size to produce accurate results while not being too fine to minimize computing time. The tip end deflection and maximum von Mises stresses, which is the value that represents multi-axial tensile stress, were compared between mesh sizes. The mesh size change between 8 and 6 millimeters produced the smallest percent change. Since the difference in the results is insignificant, we chose the larger 8 millimeters mesh size to save computing time. A convergence study was also conducted for the XFLR5 model to determine the number of X and Y panels required for accurate results. To find the required number of X panels, the coefficient of pressure was compared at various points along the foil. Between 100 and 150 X panels, the percent difference of the coefficient of pressure dropped below 5%, which was sufficient for convergence. Assuming the difference between 100 and 150 panels was insignificant, 100 X panels was used for the XFLR5 simulations. For the number of Y panels needed for the simulation, the convergence study showed that the values converged immediately with one Y panel over the span of the foil. As a result, one Y panel was used for the analysis. The maximum twist angle of the foil relative to the composite fiber orientation was first investigated. On the Y-axis, the maximum twist in degrees is shown, while on the X-axis, the fiber orientation in degrees is shown. A fiber orientation of 0 degrees is perpendicular to the span of the foil, while 90 degrees is along the span. The 66-degree ply angle showed the greatest amount of downward tip end twist, while the negative 60-degree ply showed the greatest amount of upward tip end twist. Contrary to expectations, the twist did not follow a symmetric trend with the fiber orientation. In fact, bending twist coupling is often asymmetric with respect to positive and negative fiber angles because the stiffness matrix changes asymmetrically due to non-zero coupling terms, like the B sub I matrix in classical laminate theory. This means that a positive 30-degree layup is not equivalent to a negative 30-degree layup in terms of overall stiffness and deformation response. Additionally, hydrodynamic forces acting off-center can further amplify asymmetry, making the foil's response differ significantly depending on fiber directionality. The deflections also followed an asymmetric trend. Steeper fiber angles showed less deflection as expected. The 66-degree layup offered 4.5 millimeters of deflection, while the negative 60-degree layup resulted in 4.3 millimeters of deflection. We then selected 3 layups for further investigation. The first one was the isotropic layup, which was conducted of 5 laminate plies with a symmetrical fiber orientation. Next, a layup featuring a 66-degree unidirectional fibers was chosen, as the 66-degree ply developed the greatest amount of tip and downward twist. Unidirectional fibers were selected for maximum bending twist coupling effects, while the 4-ounce cloth was included to improve the strength of the layup. A layup featuring negative 60-degree unidirectional fibers was chosen, as the negative 60-degree ply angle developed the greatest tip end upward twist. These foils were then compared to a foil producing an elliptical lift distribution and one producing a bell-shaped lift distribution. A comparison of the span-wise twist of the foils can be seen in this graph. The twist distribution of the foil producing a bell-shaped lift distribution can be seen here. The foil requires nonlinear twist with a progressively increasing rate of twist. The foil with a 66-degree layup experienced the highest rate of twist near the root, which progressively leveled off near the tip. The foil with a negative 60-degree layup also experienced a leveling off in twist near the tip. However, the twist was positive along the entire span of the foil. The isotropic foil follows the theory near the root, but the twist begins to level off and deviate around 27% of the span from the root. Increasing progressive twist was not achieved for any of the foils we tested. Here you can see the span-wise deflection distribution. The deflections were calculated based off of the average deflection of the leading edge and the trailing edge in the vertical direction. The foil with a 66-degree layup can be seen here. The foil with a negative 60-degree layup can be seen here, and the isotropic foil can be seen here. Shallower angles resulted in more deflection, as we saw earlier. The maximum stress in the composite foil was also checked to ensure that the foil design was viable and wouldn't break. The Y direction along the span of the foil was a primary concern for failure, but the maximum stress was well below the yield strength of the composite, resulting in a safety factor of 43. In order to compare the lift distribution of the foils with an equal amount of overall lift, the angle of attack of the elliptical foil and bell-shaped lift distribution foil were varied. The angle of attack of the foil with the bell-shaped lift distribution had to be increased significantly, resulting in a lift distribution that was less bell-shaped. This is because with positive angles of attack, the end of the foil started generating some lift. The lift distribution of the negative 60-degree ply foil was found to be virtually the same as that of the elliptical lift distribution. For the foil with the isotropic layout, the resulting lift distribution deviated slightly from the lift distribution, as you can see here and here. The foil with the 66-degree layout showed the greatest deviation from the elliptical lift distribution, since it produced the greatest amount of twist. The efficiencies of the foils were also compared using coefficient of lift to coefficient of drag ratio. We found that a greater twist resulted in lower efficiency, and increasing the angle of attack required to compensate for the tip end down twist produced the same overall amount of lift, reduced the foil efficiency. The lower efficiency was understandable because Prandtl's theory requires increasing the span of the foil with a bell-shaped lift distribution to achieve the same amount of lift while reducing drag. Relying on increasing the angle of attack results in a significantly less efficient foil. A limitation of our efficiency analysis was that only one angle of attack was investigated for each foil. Results from more angles of attack would provide a better indication of overall performance. From our investigation, we concluded the following: that the fiber angle resulting in the greatest amount of downward twist was 66 degrees. The composite foils were not able to achieve the theoretical twist distribution in any of the cases. The nose down twist still causes higher lift near the root and lower lift near the tip, but not to the extent of the theory. It is difficult to gauge the performance effects of this twist considering the total lift decreases in parallel. All three deformed foils with equal span and aspect ratio were found to have lower lift to drag ratio than the foil with the elliptical lift distribution. For future work, we recommend conducting a validation study by testing the foil layups in the Webflow channel to ensure that the procedure used in this study is accurate. We also recommend developing an automated iteration method to significantly reduce the time needed for running iterations. Mapping out lift and drag coefficients resulting from various angles of attack would help better understand the efficiency of the layups and foil designs. Finally, various foil sections could be investigated, and testing varying laminate thicknesses along different areas of the foil would also be interesting. And that concludes our thesis presentation. Thank you for your attention. Since this is the final presentation of our senior theses, I'd also like to thank the faculty and staff and all my classmates for support and feedback along the way. Congratulations, everyone. We made it.